Hello everyone. Let's continue our discussion about capacitors. Hopefully after this lecture we get to a point that we can start analyzing circuits with capacitors completely, including solving the differential equation that we discussed last time. But before we get there, we need to do a little bit more to get more comfortable with the mathematics associated with the equation that describes the voltage across the capacitor as a function of the current, or the other way around. So we mentioned that with the capacitor, the current and the voltage of the capacitor are functions of time, even if the voltage and current, even if the voltage across the device is a constant voltage, still because of this, the physics of the device, the current would be a function of time. So from now on, we always remind ourselves that when we write the equations, including the capacitor, we have to have a dependency on time. And we figured that the relationship goes like this. If you write the current that is passing through the capacitor is basically as a constant, which is, by the definition, is the capacitance value in the units of farads, times derivative of the voltage across the capacitor with respect to time. Again, in some books it says C dV dt. This is the same thing, just Vt or Vct for that matter. If you define Vct, the voltage of the capacitor, as V1t minus V2t, this would be the same equation. The reason that I insist upon writing V1t minus V2t is that sometimes students kind of forget about the fact that the voltage is a differential concept, and assume that this voltage in this equation or any other equation is the potential of one end of the capacitor, and that creates a lot of confusion. With this, putting it in there, we always emphasize on the fact that the voltage is actually a difference between the two potential on the two sides. Okay, with that, we can start manipulating this equation and get to other useful results. For example, I can say that ICT dt just multiplying both sides by dt at this point, both sides of this equation. dt is equal to, actually 1 over c ICT dt is equal to d v1t minus v2t. Now, if I assume that the starting point for my analysis is t equal to 0, I can integrate both sides of this equation and quickly figure out that v1t d v1t minus v2t integral is equal to 1 over c integral of ICT dt. And this would tell you from a t equal to 0 to a t equal to t. We can change that to t1 and say that that's t. Then this would tell you that v1 minus v2, v1t minus v2t minus v1 0 minus v2 0 is equal to 1 over c integral of ICT d ICT1 dt from 0 to t1 equal to t. So with this, you know that the voltage across the capacitor, you can calculate that by integrating the current starting from your initial time all the way to the point that you want to calculate the voltage But for that, you have to know what the initial value of the voltage, in other words, the voltage across the capacitor at time equals 0 is, in order to be able to calculate your voltage. And this is just because of the way that this current and voltage are associated to each other. So this equation is sometimes useful. If you define that as VCT, you can rewrite the same thing by saying that VCT is equal to 1 over C integral of T from 0 to T1 from 0 to T1 T of IC T1 dt1. Plus, that goes to the other side, VC0. Okay, so you take the integral of the current, 1 over capacitance times 1 over capacitance, added to the initial voltage across the capacitor. You can calculate the voltage of the capacitor at any point, and sometimes that becomes handy. Now, you can continue manipulating the same equation and show other equations. I'll don't go into details, but one of the other things that you can actually calculate from this equation is that the energy that is stored in the capacitor is equal to 1/2 capacitance times the voltage of the capacitor to the power of 2, and that's not hard to do. To do that, you can actually remind yourself that the power, which is dW dt, is equal to the voltage of the capacitor VC times the current of the capacitor IC. Then use this equation, put it in there, and integrate that equation, and you get to the same conclusion. This is actually quite a useful equation. So you take, once you have the voltage of a capacitor, you can calculate how much energy is stored in the capacitor, which goes is a quadratic function of the voltage. Is the voltage to the power of 2. It's proportional to the voltage to the power of 2. Okay, with all of that, I'm going to show you a few useful calculations for a capacitor. So if you recall, once we defined resistors back closer to the beginning of these series of lectures, immediately after that we discussed the resistive circuits, and we mentioned that once you put the networks of resistors, connect them to each other, and look into how you can calculate an equivalent for those networks, so that you can represent the same functionality using only one resistor. We came up with rules that would quickly simplify resistive networks. We can actually replicate the same thing with capacitors, and sometimes those come quite handy. So I'm going to show you how you can do that with capacitors in parallel and capacitor in series. Let me get rid of some of these calculations that we had to do. I'm going to leave the conclusions in there. So that conclusion and this conclusion, I'm going to leave it there, but start doing capacitors in parallel and series. So if I have two capacitors in parallel, and then we can see, so C1 and C2. And then I look into these two capacitors, and I want to turn it into an equivalent capacitor that behaves the same. We mentioned that when we talk about equivalency, what we mean is that if I take this box and replace it with another box that only have a capacitor, once they behave the same, then these are equivalent, meaning that if I apply any voltage here and apply the same voltage here and look at the currents and I see the same thing, that means I have an equivalent, right? So if I put one capacitor and call that C equivalent in this case, then if I connect this to a voltage and connect this to the same voltage, let's say I'm connecting it to a test voltage, VT, then look at the current IT going in there. And now these, I'm going to redo them with what we mentioned, Vt function of time, It function of time. If I do the same thing here, Vt, and I get the same It, then I know that these two are equivalent to each other. So let's analyze this circuit and see how we can find an equation that tells me what the equivalent of these two capacitors are. So we're going back to do simple circuit analysis. So how did we do that? So we labeled the circuits. So let's say that's these are two of my nodes. Now I know that this is Vt, writing the equation for that component. This is It. I'm going to assume that's my ground. There are two currents for these two capacitors, IC1T and IC2T, right? The two currents passing through the capacitor. Now, I write the equation for KCL for that node. I don't have to write it for this one, and then write the equation for those two components. So KCL for that node, KCL, tells me that IT is equal to IC1T plus IC2T, right? The current going into that node is equal to the two currents leaving that node. Then I write the equation for the three components. This one I already did by calling that node Vt. I've already written the equation for that component, so these two are left. This is the equation for those two components. So let me repeat, equations for components. IC1T is equal to C1, using that, D, voltage on top, Vt, minus voltage on the bottom, 0, dt, right? Same for the second one. IC2T is equal to C2D, voltage on top, Vt, minus voltage at the bottom, 0, dt. Now, I take these two, put it in the KCL. So, It is equal to C1 dVt dt plus C2 dVt dt, which means it's equal to C1 plus C2 dVt dt. Now, if I write the equation for this circuit, what do you think the result is? Simple. That's my ground, let's say. That's my Vt. And there's only one current in this circuit, and that's It passing through the equivalent circuit. So if I write the equation for that one would be It, this is now the equation for the second circuit. It is equal to C equivalent times D, the voltage of that top, dVt, minus voltage at the bottom, 0, dt. And I'm saying these two have to give me the same result. So the top one is giving me It is C1 plus C2 dV dt. The bottom one gives me It is equal to C equivalent dV dt. So if these two are the same, that means that C equivalent has to be equal to C1 plus C2. Okay? So simply, I proved that if I put these two capacitors in parallel, and what was the meaning of the parallel? That meant that the two components share nodes on both sides. So they share one node on top and share same node on the bottom. So if they're in parallel to each other, you can take the two, turn it into one equivalent capacitance, and the value for that one equivalent capacitor is basically the value of the capacitance for each one added to each other. So that may sound a bit strange in a sense that with resistors, when we put them in series, the value of the resistance added to each other. Whereas here, as you can see, with capacitors, when you put them in parallel, the value of the capacitance actually add up to be the same value for the equivalency. Keep in mind that this is, if you look at the equation for the capacitance, that shouldn't come out as a surprise to you, because if you remember with the resistor, the equation that relate the voltage to the current was a linear equation, and it was called the Ohm law. It was V1 on one side minus the V2 on the other side. It's equal to a resistance times the current. Now, if you kind of manipulate this, and this is what you see. This is the derivative of voltage on one side minus the derivative of voltage on the other side. It's kind of current multiplied by dt, but 1 over c. See, it appears as if the correspondency between this equation and what we had with the linear equation of the resistance goes like 1 over c should behave something like a resistance. And later on we're going to see that that's actually quite close to what this conclusion, kind of a intuitive conclusion, makes a lot of sense. So that's then shouldn't be too surprising to see that when you want to when you add capacitors, it's when you put them in parallel to each other. And physically speaking, this also makes sense, because if you think of these capacitors as just plates that are brought close to each other, putting them in parallel, it's the same thing as saying I'm extending these plates to become larger, right? So if they're becoming larger when you're in parallel to each other, for the same voltage, they're going to hold more charge, which means their capacitance is going up, and that's why they're being added up. Okay, so let's say these two capacitors are exactly the same. So these two capacitors are the same. It's as if you're taking one of these capacitors and doubling the area of the plates. So with that, obviously, with the same voltage, the amount of charge that you're going to collect is going to be twice as much. The area of the plate is twice, and therefore the equivalent capacitance is twice as much, or you're adding the capacitance to each other. Now, you can prove that when you put the capacitors in series to each other, then the value of the capacitance, the equivalent capacitance, is going to be calculated the same way that the value of equivalent resistance would be calculated when you put them in parallel. In other words, 1 over C equivalent when they're in series is equal to 1 over C1 plus 1 over C2. And you can quickly, we're going to quickly actually prove that too. I'm going to stop this and come back with that. So, okay, when you put the capacitors in series, just wrote it down so that we can quickly go through it. We do the same. We label the circuit, and I call that my ground or zero. That's VT from the equation for that component. I call that V1, and the same current is passing through all three components. There's no KCL to write for that circuit. I only write the equations for components. So this is the equation for that component. Notice that the voltage across that capacitor is VT minus V1T, and the voltage across this capacitor is just V1T minus 0, so these two. Now, I want a relationship between VT and IT to calculate the equivalency for that one, so I have to get rid of V1 from these two, and it would be the same thing as if you had normal linear algebraic equations. So from this one, I know dV1 dt is 1 over CIT. Now I take this and replace that in that equation. So IT from this one is C1 dV dt minus C1 dV1 dt. But now I take dV1 dt and replace it. I get that, move it to the other side, and this is the resulting equation that now relates IT to dV dt. So this value right here is the equivalent capacitance for each two. And if you notice, it's very much similar to the equation that we derived for the resistors in parallel. In other words, the equivalent capacitance for two capacitors in series to each other is smaller than each one of the capacitors. Now, that makes sense. When we put capacitors in parallel, we made sense of that intuitively by noticing that it's as if I'm increasing the area for each one of the plates of the capacitors, and that means that the capacitance is going up. But when you put them in series, you have to notice that the charge that you accumulate for each one is going to be the same, right? but the voltage that you apply across the two of them gets divided between the two, right? So if you take one of these and apply the voltage, obviously the charge that you accumulate is going to be larger than the time that you take the same voltage and apply to both of them, because now each one of these is experiencing a lower voltage, and therefore the amount of charge that is going to be collected is smaller, and this amount of charge is the same for both of them. So the equivalent of these two capacitors would be something as smaller than each one of them. And the equation or the math would tell us the same thing. Now you can take these two and expand or extend that for more than two capacitors, which would tell you that if you put n capacitors in parallel to each other doing exactly the same math or analysis, you realize that the equivalent capacitance is just all of those capacitors added to each other. And if you put more than 2 or n capacitors in series, 1 over C equivalent would be equal to 1 over C1 plus 1 over C2 plus 1 over C3 all the way to 1 over Cn if you have n of those in series to each other. With that, I'm going to stop, and we move on next to doing circuit analysis using capacitors, and this time also add at the end the solution for the differential equation, so that we can actually look at how the voltages and currents really change in a circuit with capacitors in it. Thank you.